Hello, everyone. I'm McKenna. I am a current junior at Stanford studying chemical engineering. And yeah, thank you for having me. And yeah, I'd love to just give a bit of an overview about my journey through sustainable research from high school and then where I am now, and then hopefully some perspectives of uh, what I think about sustainable research in the future. And so, yeah, I'm just going to start off with a story. And so I hope most of you know what this is. It pretty much grows anywhere and everywhere very quickly. And I'm from Phoenix, Arizona, and so of course algae grows everywhere there. And so when I was in 8th grade, my grandpa was super into outdoor fish ponds and building outdoor fish ponds. And so he's like, "Okay, McKenna, let's build an outdoor fish pond." I'm like, "Okay, of course, why not? I'm in 8th grade, so heck, let's do it." And so when we built the fish pond, of course, what showed up a couple days later is algae. And so my sister and we like scraped it all off the rocks because we had built rocks, and it was literally looked like this picture on the right. And so we have this giant pile of algae sitting right in front of us. And we look at each other and like, let's do something with this algae. What can we do with it? It literally grows anywhere. And so then upon further research, we discovered that algae actually is used for biofuels. But not only biofuels, but so much more. You may have heard of some of these applications before. And so algae can grow in wastewater and clean it up, which a project at Arizona State University actually does. It also sequesters carbon dioxide from the air, and so helps remediate effects of global warming. It can provide fish food for the fish industry. It can also provide baby milk, formula milk, and so algae is very dense in proteins, and so these proteins can be extracted and then turned into baby milk. So it's not white algae. It's the proteins inside of the algae that are put inside of baby milk formula. In case you were concerned, maybe your babies of the future could drink algae milk. And then, of course, it can be used for biofuels, gasoline, jet fuels. There's even projects that work on using algae fuel to generate electricity. So you may be wondering, okay, this is cool, but I've never seen any of these products in the real world. So yeah, what's up with that? And algae is actually extremely expensive. So it's expensive to process, to grow, to actually get the proteins and oil out of the cell. And part of this is because there has a really tough cell wall. And then additionally, algae is just a little bit difficult to grow on mass scale because you have to stir it, you have to put in nutrients. It's very complicated. So of course it's very expensive. And so in high school, I decided to do a lot of science research and projects on how do we make algae economically feasible? How can we decrease the cost of algae so that people can obtain the value from algae? And by decreasing the cost, it may be the only way we can bring the value of algae to the world. So in 2017, which is the year I won the Walton Sustainability Award, is when I worked on this project with algae extraction. And so just a little bit of background, in case for anyone who's unfamiliar, is algae grows like any other organism. It photosynthesizes like a plant. And then when it gets stressed out, it will produce lipid bodies, which is like fat storage. So it's like a polar bear storing up fat for the winter. And it gets stressed out and it starts putting all of its energy into producing lipids, which is oil. And so then we can remove that oil from the algae cell and then convert it into a biofuel, which is like a gasoline. But the problem is it's very, very difficult to break through that cell wall and obtain all of that oil inside of the algae cell. So there's lots of different ways of doing this, and so I wanted to compare all of them, plus try out some new ideas that I had, or have fun in the lab with it and see, can we get the oil out of the cell using no energy and at a very low cost? That was my goal. And so through like prior research, through reading literature, one of the best ways of weakening the cell wall of the algae is with enzymes. And so these enzymes can break down the cell wall or weaken it by breaking, because cellulase, for example, will break down the cellulose. That is a big factor in some strains of algae. And so then if you weaken the cell wall, it's a lot easier to pull that oil out with chemical solvents, for example. and you don't need as much energy. But of course, with all things algae, enzymes are ridiculously expensive because they have to go through their own manufacturing process. And so I was like, let's just skip that step. Can we just skip the enzyme processing step? I really just need the enzymes. So I found this fungus, Aspergillus niger, which is a very common fungus. And if you see mold, chances are it could be this. It grows on potatoes. And so I was like, okay, let's just see, can we make this fungus produce a ton of enzymes that may break down the cell wall of the algae and then put that growth medium that the fungus release the enzymes in with the algae, and then let it see if we get the oil out. So it turns out it worked, and which was super exciting because by being able to weaken the cell wall with these mixture of enzymes that this fungus is producing, I was then able to obtain 95% around of the oil that was inside of the algae cell with no additional energy and at a very low cost. So then the next year, I was like, okay, let's take this further. How can we take this further? Now can we decrease the cost of growing algae? And so you may be familiar with the lichen, which is a very common and hardy organism in the world. And it forms the basis of many ecosystems, and it capitalizes on the symbiotic relationship between algae and fungus. So the idea is that the fungus provides a home and protection for the algae, and the algae is providing oxygen, the fungus is providing carbon dioxide and food, and it's like this beautiful network. And it's a lot of it is misunderstood, not researched fully, but we do know that they grow really well together. So my idea was, okay, let's see if the algae and fungus can grow together super well, and then once the algae grows up a lot to a high concentration, let's turn the fungus against it and make it release these enzymes that then will break down the cell wall and weaken it. And so the cool thing was the algae and the fungus did grow really well together. So here's a picture on the left. And you can see even without agitating the water. And so one of the biggest requirements for algae growth is you got to move the pond around. You got to move the algae because it doesn't like to stay still. But with the fungus, it would actually even grow without even stimulating the water. So that's very interesting, and not something that I completely understand fully yet is why that happens. And then this is the agitated fungus and algae together. And so you can see here, it's like, how did the algae grow so well? Like, what is going on here? How is the fungus helping this algae grow? And so if you're curious about the microscope slide, this is the algae cells growing near the network of the fungus, and this brown one is the fungal cell. So it almost seemed like the algae was growing on top of the fungus, but yeah, why does that happen, and how do they grow well together? But one thing, even though I didn't understand the mechanism of it, could see that yes, by using fungus with algae, you can get a higher concentration of algae, so you can lower the cost. You don't have to use additional energy because you can extract the algae oil using the fungus, and you're capitalizing on a natural environment, and you can obtain maximum oil yields from the algae cell. And other methods, it takes a lot of energy to obtain the same results. And then even further, you're like, goodness, there's so many benefits with this method. Like, why don't we see it yet? And because it even can grow on wastewater. And so when I went to college, I was like, okay, we gotta, let's do this. Let's see what is the potential of algae. And so focused then on why. Why does the algae grow better with other organisms? And so Stanford, we have it's a research wastewater plant, and it gets its wastewater from the dormitory. So I always would joke around with my friends, like, haha, I'm growing algae on your waste. And they would think I was weird. And so surprising that I had friends when I told them that I was growing algae on their waste. But anyways, a little fun story. So you can see here that the algae grows better with the bacteria, probably even to more of an extent than with the fungus. And so the picture on the left here, the vial on the left has no bacteria in it, and the one on the right is algae with the natural wastewater bacteria. So super cool, and this is after about 3 days. You can see that the algae and bacteria grow to great concentrations. They even have some flocks, which you can see in here, the little specks, which helps with harvesting the algae. And then the picture on the bottom is, again, the 3 on the left are with the bacteria, and the 3 on the right are without. And so somehow this bacteria is enhancing the growth of this algae. And so then did some research. Is it just one bacteria? Is it multiple? And so conclusions I made were, yes, it's a consortia of several bacteria strains, potentially even fungus as well, aiding this growth of algae. So algae loves to grow with friends. And so by learning about how these organisms interact with each other, we can better grow algae more efficiently and at lower cost just by using other organisms. And so humans don't really have to do all the work that we thought we had to do. And so by working in this lab of, it's a microbiology lab at Stanford, and by learning about what other researchers are doing and also learning about microbiology, found that microbes are incredible. They are powerhouses and they can do all kinds of things. So you may be familiar with some of these applications, but microbes can, they produce insulin for diabetes. It's like yeast, which produces pizza and bread, which many of us like. And then it also can produce vitamins, which are good for improving health. And then even a cool project I found is using bacteria to produce textile fibers that then can be used in making clothes. So like, okay, this is cool, but they can also have huge environmental impact. And so microbes can grow in wastewater, break down components of the wastewater that are harmful to the environment. You can use microbes to break down trash in landfills to then produce energy from our trash. You can create biofuels with microbes, like when growing with algae or other biofuel crops. And then even interestingly enough is they can produce proteins, which then can be made into vegan meat. So we may have bacteria meat coming soon. I know that's not a very catchy slogan, but anyways, the possibilities of microbes are endless. But the problem is, or one of the downsides to microbes is we really just know about these fast growers that are easy to study. They grow really well in the lab and they grow really efficiently. You may have heard of E. coli. It's used in a lot of high school labs and experiments. And E. coli is really good at growing. It's really fast and we get our research done quickly. We can get our publications out. But what about these slow growers? Most of the microbes living in the world are slower growers, but they're extremely efficient because like how do microorganisms grow in the deep sea? They have to grow under really harsh conditions with very few nutrients. And somehow they've evolved to grow. And so it gives researchers a desire to understand how are these slower organisms able to survive when there are hardly any nutrients around? And then how are these organisms interacting with each other? How do they grow amongst a group of all different kinds of species? And so a lot of this is difficult to study using current lab methods. And so I'm currently working on a method that will allow lab environments to efficiently isolate these slower growing organisms and then study them by protecting them from neighboring organisms. And you may be thinking, well, that's extremely specific and that is extremely niche. Well, okay, why? Who cares? And so I like to think about the bigger picture of things. Why would we focus all of our money and resources into decreasing the cost of algae when we already have gasoline that works fine? And I don't think it's going to run out anytime soon. Maybe you do. I don't know. It's unknown. It's not running out anytime soon. But why would we spend time looking at all of this? And so I want to introduce you to, which you may have heard of this before, but a professor introduced it to me my first year at Stanford, and it's the food, water, and energy nexus. And so the idea is that each sector is connected to another. So for example, energy and food sectors are connected because we have energy crops, food production requires energy, we have to transport food around, we have to process the food, all of which requires energy. And then food and water are connected because you need water to grow the crops. And maybe you grow fish in the water, water quality, we drink water. And so all these sectors are connected. And most of the time, humans for the past thousands of years were really good at maximizing efficiency in one sector. So let's just take energy as a case study. So we are really good at producing energy. Let's go down into the ground, drill some oil, create gasoline, and now awesome. Now just a couple tanks of gas, we can drive across the entire United States. That's incredible. But what have we done? We've released carbon emissions, caused global warming, acidified our water supply, endless environmental problems because of that. And so the food, water, energy nexus is about combining one process with all of these sectors. And so algae, for example, is a great connector of these sectors because it provides energy, it grows on wastewater, and you can even eat it. So if you separate the protein and the lipids from it, you can get oil and you can get proteins out of the same algae source. And so I'm a huge proponent that microorganisms can connect this food, water, energy nexus. But still, you might be like, okay, what really does the food, water, energy nexus look like? It sounds very abstract, which you're right, it is a bit abstract. So here's just an example. Okay, so say we want to build a house, and part of sustainability goals is providing housing and shelter for everyone around the world. And so say we want to provide a house for a vulnerable population, and then they also are going to have a dairy farm. And the idea is that the dairy farm would be able to produce milk, and then they can go and sell the milk in the market and produce money so that they can live. Cool. All right, now let's just stop at that system. We got really good at producing milk and money. So cool, we're done. No, but there's more. The cows are going to produce a lot of waste, and maybe we would just throw it away. But maybe we could also put it in an anaerobic digester, which capitalizes on microorganisms, and these microorganisms can produce energy using and from that waste. Cool, so now we can have that energy that came from the cows that is now going back and powering the house and powering the dairy farm. Okay, but then what next? After the bacteria grow on this manure here, we create wastewater. And now we have a lot of nitrogen and phosphorus. And okay, should we just put this into the ocean? No, we can do more with it. What can we do? We can grow algae on it and bacteria. And so then we can create the clean water from it. And then we also get the algae. And the algae, as I said before, can provide protein, it can provide more biofuels or more energy, or we could repurpose it into feed for the cows. And then the water can also be recycled, go back to the house. Maybe it's for running water for washing clothes or for going to the bathroom. And then it can also be water for irrigation or for the dairy farm. So you see here how by using our waste, we can connect all these sectors together. And instead of just getting really good at doing one thing, we can produce many things. And this is what helps create cost-efficient, energy-efficient, and sustainable solutions. And I'm a huge proponent for microorganisms and how they can connect these sectors together, because you saw how microorganisms love eating waste. Thank goodness for microorganisms, because they clean up a lot of our messes. And they also provide a lot of value for us. And so we can harness the power of these microorganisms from our waste and then create even more value from it. And so that's why I titled the presentation The Value in the Overlooked, because there's so much value that we are just waiting to uncover in our own waste even. And so I would challenge you all to look around you and what things are just going to waste or you throwing away that you can actually use, not just to impact the environment, but also to create a cost-efficient and beneficial product for human use even. And so I'll leave you all with that. And thank you so much for having me. And it may seem way out there, things that I talked about, like that's research that's way out of here, out of my scope, out of my mind. Does it affect me? But who knows? Maybe one day you will find an interest in microbiology, or in somehow or way of another, you will also be working to connect the food, water, and energy sectors together. And so good luck with the rest of your fair. And thank you so much for having me. And yeah, have a good day.